Goes on topic 2.2, intermolecular forces and potential energy. Today we're going to talk about potential energy curves for covalent bonds and how Coulomb's law can be applied to ionic bonds. My name is Alice Pudi and I'm happy to be back with you on AP Daily. For a chemical bond, this is the attraction between the nucleus of one atom and the electron of another. So this is different than ionization energy, where those attractions, we were talking about the nucleus and electrons of the same atom. And in a chemical bond, there is a balance between attractive and repulsive forces. So when we talk about attractive forces, now we're talking about the nucleus of one atom and the electron of a different atom, and then the same thing, nucleus of this atom, electron of this atom. So those would be attractive forces. For repulsive forces, then it means the nucleus or protons of both atoms or the electrons of the two different atoms as well. This is a potential energy curve for covalent compounds. And so if we look on the x-axis, this is internuclear distance. So what that means is the distance between one nucleus or the two different nuclei within the same bond. And this is measured in picometers. On the y-axis, we have potential energy, and this is measured in kilojoules per mole. If your energy, potential energy here, is greater than 0, what that indicates is that we have an unstable atom arrangement. If it is less than 0, then that indicates that this is a stable arrangement. And we're going to talk about is the bond formation for hydrogen. And so right now I have two hydrogen atoms and they are far apart, which means there are no attractive or repulsive forces, and the potential energy is going to equal 0. As the hydrogens get closer together, there are going to be some of both types of forces, and you can see that the potential energy is decreasing, indicating that this is a more stable arrangement. And then when we get down here, notice that we have the lowest potential energy, and now we've reached a balance between these attractive and repulsive forces, and this is a stable arrangement. So let's talk about what happens when the atoms are at this point. So the first thing is the bond energy. If I look on the y-axis, this represents then the energy required to break the bond. Now, if you're already familiar with bond energy, you know that bond breaking is an endothermic process. And so this value should be positive because to break a bond requires energy. And so how can this energy be negative? And that's because remember that this diagram is about bond formation. And so the bond energy would be the same value, but it would just have the opposite sign. If I look on the x-axis now, this is then the distance, and so this represents the bond length between my two hydrogens. If the hydrogen atoms come even closer together, then what happens is now the atoms start to feel strong repulsive forces between them. The potential energy is now greater than 0, and this would be an unstable arrangement. Next, we're going to take a look at bond order, length, and strength. So what I have here is representations of a single bond, double bond, and triple bond. And so for a single bond, it shares the fewest number of electrons. So you can see that there are 2 here, which means there's a weak attraction between the nucleus of one atom and the bonding electrons, and that's going to result in a longer bond. For a triple bond, we have then 6 electrons. So this means that more electrons results in a stronger attraction between the nucleus and your bonding electrons, and that's going to result in a shorter bond. For ionic bonds, this is the electrostatic attraction between your cations, which are positively charged, and anions that are negatively charged. Back in an earlier lesson, we talked about Coulomb's law, and at that point, we talked about the attractive forces between the nucleus and electrons, so our charged particles, and now Coulomb's law is going to apply in the same way, but now we're going to discuss it for cations and anions, where Q would be the charge on one of the ions, Q2 is the charge on the second ion, and R is the distance between them. But we have the same conclusions that we had before regarding larger ions, meaning stronger forces of attraction, and greater distance, meaning smaller forces of attraction. Okay, so let's go ahead and take a look at an example. So what I have here is a potential energy diagram for an XY single bond. And you can see where the bond energy is for this bond and the bond length is for this particular bond. And if we compare this then to an XY double bond, which is the red curve, now notice that the bond energy is significantly greater and the bond length has now shortened. And that's because now there are more electrons being shared that's resulting in the stronger bond. This is the end of the video. Thank you for watching. Please join me for the next video, which will look at practice questions on potential energy